Hi folks, we are back here. So today is the 23rd of July and we are going to talk about now the thermodynamic processes for an ideal gas. Chapter 15.3. Okay, this chapter here uses a concept that I didn't cover yet, a concept that in 14.4 in your book. Let's take a look. Section 14.4, specific heat of ideal gases. Okay, in this chapter we introduced a new type of specific heat. And we're going to use this new idea that I didn't cover before. So just keep in mind that for the next exam, this chapter will also show up. Okay, 14.4. It didn't, I skipped it for the first exam, but we need to cover it for this new chapter here, this new section. Let's go back here, 15.3. Okay, so let's just come up with a little table just to refresh your memory. Okay, so what we had before, we defined the following quantities, which are very useful, by the way, which are very useful, right? So what are the quantities that we defined? First, we defined the heat capacity. Here you go. The heat capacity is defined by the amount of heat that goes into the system per change in temperature. Okay? And then we define a new. By the way, this definition of heat capacity applies not just to solids and liquids, but apply to gases as well. Okay, just keep in mind that this definition of heat capacity applies not just to solids and liquids, but also to gases. Okay. So what else did I define to you? I defined to you something else that we call a specific heat. A specific heat capacity, which I call it denoted it with a small c. And what is the specific heat capacity? The specific heat capacity is the heat capacity divided by the mass of the substance. Something like that. Like that. Okay, that's the specific heat capacity. That's the heat capacity. And now we're going to define a new type of specific heat capacity. We can say that this one here that you saw that I saw right now is the mass specific heat capacity because it's divided by the mass. Okay. But then I'm going to define a new type of a specific heat. That's not a mass specific heat capacity, but it is a molar specific heat capacity. This definition, the definition for this type of heat is very useful for gases, especially when it comes to gases. There are two types of molar specific heat capacity. Two types. Remember that because we are talking to gases, because we are talking about gases, there is the molar specific heat capacity at constant volume, that is defined as a C over V. And how do we define that? Okay, it's going to be the specific heat capacity it's going to be the heat capacity divided by the number of moles of the gas. Here you go. And then molar specific heat capacity at constant volume. And then there is the molar specific heat capacity at constant pressure. So two types of a specific heat capacity. Okay, so it works like that. Here you go. The specific heat capacity at constant volume. Okay, that's the equation for a specific heat capacity. And then there is also the specific heat capacity at constant pressure that for now I'm going just to abbreviate as CP. I'm going to show to you how we can get the CP, okay? But let's concentrate on this one. Let's concentrate on this one here. So what we're going to do, we are going to calculate what is the internal energy and the change of internal energy of a gas under a thermodynamic process that of constant volume, that one at a constant volume, delta V equal to 0. We did that before, but we didn't do it specifically for an ideal gas, right? We're going to do that specifically for an ideal gas. You know from the previous section that at constant volume, the work done on the gas is 0. And because the work done on the gas is 0, the change in internal energy is going to be due only to the heat. Okay? And then, but this heat can be rewritten in terms of the specific heat capacity at constant volume. Let's take a look at that. Okay, let's get this equation here. The molar specific heat capacity, don't forget the molar specific heat capacity at constant volume. Okay, we can here write that as being what? Here you go. It's going to be CV and delta T. But don't forget that will be the Q, right? But don't forget that the change in internal energy is also equal to Q whenever you have a constant volume. There's no work done on the gas, right? So the subscript V on the symbol, for molar heat capacity was added to remind you that the process was done at constant volume. So let's just go ahead and do our little table here so you can remember more easily what types of heat capacity we have. Okay? Heat capacity, here. We have heat capacity, which is defined as like that. We don't need we have a specific heat capacity, which we gotta represent that by C, right? We have a specific heat capacity. And now we have the new one, molar heat capacity at constant volume, constant V, or constant volume. It's nothing but the heat capacity divided by the moles, right? So here we go. I'm going to copy this one right in here. And I'm just, if this one here is C divided by M, this one here is going to be C divided by N, the number of moles of the gas. Different types of heat capacity. It's always good to keep them side by side so you can associate something that's new with something that you already know, right? It's always good to do something like that. So that's the one that we're dealing with, and this one is most useful with gases. More useful for gases. You can put that between parentheses like that. Okay, what else can we do about this equation here? Okay, so let's go back to this equation. Okay. Instead of talking about change in internal energy, don't forget change in internal energy, which is the delta U here that we use. Internal energy. We can talk about actual internal energy. Okay. Or represented just by the letter U. How do we do that? Okay. Well, just be reminded that at 0 Kelvin, there is no motion whatsoever of the molecules that make up a gas. And because of that, there is no kinetic energy associated to those molecules. So at this point, when the temperature is equal to 0 Kelvin, it's reasonable to say that the internal energy of the gas is equal to 0. Okay? So it is reasonable to state that the internal energy of a gas at T 0 Kelvin is 0. So what do we do? So we define the actual internal energy as the following, the actual internal energy of the gas. Don't forget, right? Here you go. Delta U is what? Delta U is the final internal energy minus initial internal energy, right? That's what delta U is all about. But let's say that the initial internal energy is the initial internal energy at 0 Kelvin. Okay? At 0 Kelvin, the initial internal energy would be 0. And now my delta T that you see here is going to be what? I'm going to copy that. It's going to be my final temperature minus my initial temperature. In this case, the initial temperature is going to be the temperature at 0 Kelvin. And now we can express the internal energy in terms of the temperature, the absolute temperature. Here you go. See that? Oh. Or, we can drop this 0 altogether, right? Dropping the subscript F, dropping the subscript F to simplify the notation, we now have that the internal energy of the gas can be expressed as, here you go, can be expressed with respect to the temperature at absolute 0. Now let's relate our molar heat capacity at constant volume with some other parameters. There is a really nice relation between the molar heat capacity at constant volume with some of those variables, some of those parameters that we saw before. Okay? Recall that we derived before the kinetic energy of a gas containing any molecules or n moles, right? Let's use this equation. That's in 14.4. Okay? So here you go. So let's recall what we did before. Here you go. We gotta go back to our kinetic energy that we derived for the gas. Which was, here you go, right in here, right? The translational kinetic energy. In this case, N, the big N, is the number of molecules that we have in there. So here you go. That's the derivation that we did right in here. Okay. Right in here. Let's copy that. It's very easy to remember this equation. It's not difficult. And I'm going to give you I'm going to show you a little trick to remember this equation. Here you go. That's the translational kinetic energy of the entire gas, right? Of all the N molecules, nRT. The higher the temperature, the faster the molecules in the gas travel. So how can you remember this relationship in a simple way? Okay, how to remember this relationship in a simple way? Okay, I want to write that down here. Recall that the translational kinetic energy of an ideal gas is given by, right, this translational kinetic energy also coincides for a monoatomic gas. Here you go, not a gas made of two atoms. No, just for a single atom gas, monatomic gas. This translational kinetic energy coincides with the internal energy of the gas. We saw that. Internal energy, we saw that before, right? Energy of the gas. Okay? So let's stick to monatomic gas first. And very soon we're going to talk about diatomic gas. Okay? So those monatomic gas, they just have motion along the x-axis, the y-axis, and the z-axis. Okay? The velocity of these gases is a combination, the velocity vector of this gas is a combination of those three vector components. Just remember that three vector components. We see the three vectors component is right in here. Okay? So in reality, how to remember this relationship in a simple way? Yeah? Just remember that a molecule or particle has three components in its velocity vector. X velocity vector, X, Y, and Z. Okay? So what we have right in here? What we have right in here is the three components of the velocity vector. Okay? So here you go. These three have, in reality, I'm not going to prove that, but where does it come here? It comes, this translational kinetic energy is a contribution of the x component of the velocity, of the kinetic energy along the x component of the velocity, the kinetic energy along the y component of the velocity, and the kinetic energy along the z component of the velocity. That's why you're getting 3.5 here. What we call that is the equipartition theorem. It's possible to prove that. We're not gonna prove that, okay? A contribution, the above equation is a representation of the contribution of each velocity component of the particle. What we call the equipartition theorem, which we are not going to. Equipartition theorem, we're not going to prove that here. Just remember that. So what are you going to do? Okay, we're going to use what you have here to find out how my CV, changes. Let's see here. I need to copy that part here. Okay, this one must go elsewhere. Hey, sorry for the little confusion here. It should go right in here. Okay? Let's go right in here. There is a very nice relationship, very simple relationship that we can get from the CV. Okay? So let's go back to this equation. Even better, let's go back to this one right here. Okay? Suppose that we apply a heat Q to a gas, something like that. When we apply heat, there will be a change in energy, a change in temperature. This change in temperature is going to cause also a change in kinetic energy. Can you picture that? Okay. The application of this heat Q will change the kinetic energy of the gas. Okay? And now it's going to change by how much? It's going to change. It's only, remember, it's only the temperature that's changing. The number of molecules of the gas is not changing. So this application of heat Q is going to change the kinetic energy according to this equation. And all this heat is going towards the kinetic energy. So what can we do? We can make my change in kinetic energy equal to Q. Okay? And then we get an interesting relation, which is the following. My delta K is something like that. And my Q is something like that. See what happens to the delta T. And see what happens to the N, okay? N cancels with N. Delta T cancels with delta T. And look what we get. We get a molar heat capacity. Remember, it's a molar heat capacity. It's not heat capacity, right? That is equal to 3/2 of a universal constant, our R. Okay, this value is possible to calculate. Is 12.5 joules per Kelvin per mole of gas. And by the way, this relationship applies to any monoatomic ideal gas. Any. It doesn't matter if it's the helium, it doesn't matter if it's the neon. Those, what do you have right in here? Those are actual measurements of this molar heat capacity as constant volume. Those are actual measurements, okay? Notice that it coincides very well for the helium. You know, changes a little bit for the neon, but it's the same for the argon gas. Okay? So here's the theory that we derived, and here are the actual data, experimental data, that shows that an incredible coincidence, incredible, not coincidence, but a very good compatibility here, right? With the theory. There are only two hundredths of a unit here, right? 2/10 of a unit here difference. That represents less than 2% of difference for the neon gas. Less than 2%. Anything less than 5% is negligible in an experimental setup. Okay? So let's go back to my notes. Here we go. This is a specific heat capacity whenever you do the calculations. Is what, 12.5 joules per Kelvin per mole. Okay? I'm going to put the Kelvin after the mole. So there is no, here you go, joules per mole per Kelvin. This value for the molar heat capacity matches within 2% the experimental, the measured values of different monoatomic ideal gases. See table, here you go, what table? 14.2 in the book. Okay. So now we have a numerical value for that, 3/2 of R. And again, this 3/2 comes from the fact that the gas has 3 components in its velocity, right? Along the x-axis, along the y-axis, and along the z-axis. So each velocity component is contributing 1/2 of R for the molar heat capacity at a constant volume. What about a diatomic gas? A gas with 2 atoms that are bound to one another. Okay, so we're going to do that for a diatomic. Okay. Diatomic gas. Okay. For a diatomic gas, the gas, no, just picture, for the atomic gas, just picture this gas molecule, the gas molecules as a dumbbell, okay? Here you go. We have this illustration right in here in the book. 2 atoms connected by a little rod, okay? For a diatomic gas, for this type of gas, it still have the same translational kinetic energy for diatomic ideal gas, right? Let's put diatomic ideal gas, yeah, monoatomic ideal gas. For diatomic ideal gas, you still have the same translational kinetic energy. Okay, just the kinetic energy is going to be given by the same equation. The center of mass of this gas will have a kinetic energy also given by that. However, this kinetic energy will not, here you go, I'm gonna not coincide with the internal energy of the gas. So why is that? The reason is simple. In addition to its kinetic energy, to its translational kinetic energy, Here, let's put that. To its translational kinetic energy, comma, the gas will also have a rotational kinetic energy. Okay? In addition to its translational kinetic energy, the gas will also have a rotational kinetic energy. Let's take a look how is the rotational kinetic energy of this gas. Here you go. The illustration here shows very nicely the gas can rotate along its axis, along its longitudinal axis, and along its two other perpendicular axes. This axis is perpendicular to this one, which is perpendicular to this one. Here, the gas is rotating along its vertical axis. And here, the gas is tumbling, right? If you consider that be my diatomic gas, suppose that we have two particles here, two atoms here at the end of this span. The gas can rotate about its own longitudinal axis, can rotate about this axis right in here, and then it can also tumble, right? Can tumble like that. Well, according to the equipartition theorem, the contribution to the kinetic energy, we're not going to prove that here, okay? We cannot prove that here, it's too much work. The contribution to this rotation, the kinetic energy contribution to this rotation and this rotation is just like the same value for the x, y, and z components, okay? But for this one here, the contribution to the rotational kinetic energy is going to be negligible. There's a very good explanation for the contribution of this gas. It's going to be almost zero. Why is that? There is a reason for that. The reason is that because we are treating the gases as though they are point particles. Point particles have no dimension whatsoever. So you cannot discern, you cannot see any rotation along this axis due to a point particle. Point particles, 2 point particles here along this axis, they do have rotation. They also have this type of rotation. They have this type of rotation, right? Picture the molecules here, the atoms here at the end. And they also have this type of rotation. But you cannot discern any rotation of a point particle along this axis here. Especially in view of the fact that this rod also is supposed to have supposed to be infinitely small. So the contribution for this type of rotation is going to be approximately zero. And the other two rotations are going to contribute the same amount of kinetic energy as the x and y and z components of the atom. Okay? So here you go. So let's go back here. In addition to its translational kinetic energy, the gas will also have a rotational kinetic energy. There are 3 possible states of rotation for a diatomic gas. Here, along its longitudinal axis, longitudinal axis, and along 2 other perpendicular axes. The contribution along the kinetic energy contribution along the longitudinal the molecule's longitudinal axis is 0 because we cannot discern the rotation of 2-point particles along this axis. It's just like saying that a point rotates, a sole point rotates. You cannot discern that, you cannot see that. However, for the other two rotations, they contributed the same amount of kinetic energy. Kinetic energy that is contributed by the x, y, and z components of the velocity. In other words, here you go. The rotational kinetic energy is going to be given by the kinetic energy along one axis and the kinetic energy along the other axis. So the net kinetic energy is going to be 2 divided by 2 nRT. I'm going to keep it in this notation. Okay? And the net kinetic energy is given by the translational is the translational plus the rotational kinetic energy. Okay, so it's going to be like that. You go net kinetic energy. I'm going to put it like that. Translational plus rotational is going to be 3/2 of nRT plus 2/2 of nRT, which is going to end up being 5/2 of nRT. That's the kinetic energy. We're still dealing with an ideal gas, remember, right? And just like before, under constant volume, we repeat the same game that we repeated here, right? Here you go. Under constant volume, here you go. The change in kinetic energy, the change in total kinetic energy is going to be 5/2 of nRT under constant volume. Okay, don't forget, this is a diatomic, I'm going to put that for a diatomic ideal gas. We have this change. Oh, wait a minute. For a diatomic ideal gas. Okay, so for a diatomic ideal gas, for a diatomic ideal gas, the net kinetic energy will be this one right here. Maybe like that. Just like before, if we apply heat to the system, here you go. We're just going to repeat what we did before. If we apply, suppose that we apply heat Q to a system, that you're going to generate a change in temperature in the gas. It's still a constant volume, right? This application of heat is going to change the kinetic energy of the gas by 5/2. At constant volume, the only contribution to the internal energy is going to be the kinetic energy. Go, I can even put delta U here as well. All right. So what we have here, 5/2 nRT. And look what we get. This is the molar heat capacity for a diatomic gas. What was 3/2 became 5/2, right? And 5/2 is what? 20.8 joules per Kelvin per mole. 20.8 joules per Kelvin per mole. How does it compare with actual experiments? This is all theory, right? But it's a very good theory. Here you go. Let's see. Diatomic. What we got? 20.8. If we have a helium-2, it's 20.4. 0.4 difference. 0.4 difference is going to be less than 2% again. Pretty good, right? 20.8 for nitrogen coincides pretty well. 21 for oxygen. Even less, the difference, even less than the one for the hydrogen atom. It's going to be 1% only for those three diatomic gases. Okay? So it's a very simple theory that provides very good results in terms of what we experience in the laboratory. Okay, so here we go. Three halves for a monatomic gas, 5/2 of R for a diatomic gas. Let's save that. Now let's get to the case of constant pressure, isobaric, ideal gas under constant pressure. Okay, so we already know that the work done on the gas is P delta V. We saw that before. Okay, when we substitute that in the equation for the change in internal energy, we get something like that as well. Q minus P delta V. Change in internal energy. And we can go further on that. Let's not forget, just like before, going back to the case of the heat applied, right? Heat applied is going to have a similar equation than as we had before. Here you go. Heat applied, Q is going to be, and in this case it's not going to be CV, it's going to be CP, to denote that's constant pressure. To remind you that what we are talking about here is constant pressure process. We can substitute this Q in the equation for the change in energy. Okay? Get something like that. And then what about here? What about here? We can here write it as well in terms of the ideal gas law. Remember the ideal gas law? Here you go. PV is nRT, right? Delta T. In this case, it's going to be delta T. A T for this V final and a T for this V initial. So I'm going to copy this one and just paste it here. I'm going to put, T final minus T initial. Take place right here. Now what we have here is exactly the same thing as this one, right? So let's go expand. Let's substitute the delta T right in here. And then we get this equation here. Put the delta T in the N and delta T in evidence. And that's what we get for the change in potential energy or the change in internal energy. That's what we get. Recall that for an ideal gas, the change in internal energy depends only on the temperature. Okay? Recall that. It comes from that equation for the kinetic energy, right? It comes from the equation for the kinetic energy, right in here. That's for a diatomic gas, right? For a monatomic gas as well. The kinetic energy, whether it's a diatomic or a monatomic ideal gas, it depends exclusively on the temperature. So it doesn't depend on the process, whether it's under constant volume or constant pressure. Here you go. So it's not just a change in internal energy, but actually the internal energy in general depends only the temperature, For a monoatomic ideal gas, right? That's the internal energy. For a diatomic ideal gas, there is only a dependence on the temperature. There is no dependence on the volume or the pressure. Note see that for either ideal gases, there is no dependence on the volume or pressure. Okay? So let's look that in the PV diagram. Let's see how it looks like at the PV diagram. Here you go. Here is just an example of a PV diagram. We have the pressure in the vertical axis and the volume in the horizontal axis. This is the case of an ideal gas. Okay, an ideal gas that kept a temperature T1, ideal gas that kept a temperature T2. What you see right in here is one of the isotherms at T1, right? PV is equal to nRT. It looks just like that. A decay is an inverse proportionality between the pressure and the volume. At a higher temperature, the isotherm looks just like that. Okay? So what you can say, what we can say about an ideal gas? We can say that if the state of the gas is right in here in this curve, the internal energy of the gas will be the same wherever it is in this isotherm. Remember, the internal energy of an ideal gas depends only on the temperature. Similarly, at a higher temperature, the internal energy here is going to be higher than the internal energy here. But the internal energy anywhere at the T2 will be the same. So that's a line of equal energies, equal internal energies. So if you have a process in which the gas go from one isotherm to another isotherm in a constant pressure process, something like that, right? Whether the process is constant pressure or constant volume, the change in internal energy is going to be the same, right? Here you go. Makes sense, right? Internal energy here is going to be the same as the internal energy here, okay? So for either ideal gases, whether the monatomic or a diatomic gas, there is no dependence on the volume or pressure. The internal energy or the change in internal energy is going to depend only on the temperature. Now we're going to get an interesting result. Okay? Recall that we got the following change in internal energy for a gas undergoing a constant volume process. Let's go back here. We got something like that, right? You go. And I'm even going to, put a subscript here to remind you this is constant volume, okay? And I'm going to put a delta T. Delta T. Similarly, for constant pressure, we also have, and again, I'm going to, in order to remind you that this process was done at constant pressure, I'm going to put a subscript P right here. If the delta T here was the same as the delta T here, then it means that the change in internal energy at constant volume is always going to be the same as the changing energy at constant pressure. Make sense? Right? Because of the above, because again, here you go. Again, because the internal energy of the gas depends only on the temperature. Okay? The change in internal energy will be the same whether the process was an isovolumetric or isobaric, provided of course the temperature changes were the same. Temperature changes were the same during both processes. Or, here you go, what we have, go, applying the relations that you see here, we can get a relationship between CV and CP for an ideal gas. Here you go. Let's go another step. The n cancels the n. We are assuming that under all the processes, under both processes, the n and delta T are the same. We have this relationship between CV and CP. Okay? That's an interesting relationship. The molar heat capacity of the gas at constant pressure is different than the molar heat capacity of the same gas at constant, that undergoes a constant volume process, thermodynamic process. And you can see that CP must be greater than CV. Now let's do this quick example here. Warming a balloon at constant pressure. Okay? So you have a balloon and filled with helium gas at 20 degrees C and 1 atmospheric pressure. Yeah. The volume is 8.5 cubic meters. And then what do? We go ahead and put a flame below the balloon, right? Have you ever seen those balloons? They have a little mouse that at the bottom, right? And they put a flame at the bottom of the balloon to fill the gas, to warm up the gas. Not to fill, but to warm up the gas. If you warm up the gas is going to expand if you keep the pressure constant. Can you picture that? The balloon expands at constant pressure. What's the heat flow into the helium? Note that we are talking about constant pressure. Okay? So let's go ahead and do this problem here in my software. Here's my software, right? Balloon at constant pressure. Balloon being warmed up. Warming up a balloon at constant, warming up a balloon at constant pressure. Find the heat transferred to the balloon. So we do know that there is a relationship between the molar heat capacity at constant pressure there's an equation for the heat that depends on the molar heat capacity at constant pressure. It's something like that, right? We also know, and by the way, the gas is a monatomic gas, monoatomic helium. The balloon is filled with a monoatomic helium gas, right? Helium gas. Let's go back here. Helium gas. Which behaves like an ideal gas. For the case of monatomic gas, ideal gas, the CV is what? The CV is 3/2 times R, right? And the CP is going to be what? We saw the equation that relates CP with CV is CV plus R. Let's take a look there before. Here you go. Here you go, CP is CV plus R. Okay? And CV is going to be what? Here you go. CV is 3/2 of R, and CP ends up being 5/2 of R. So we can substitute that here, and we get 5/2 of R. So we got our part of our equation solved here. Okay, we know what the delta T is, we know our R is. What we do not know is the N. That we do not know. How do we find the N? You know, the N we find by using the ideal gas law. Let's do that. Here you go. P times V equal to NR times T. Right? But let's not forget, it's going to be final P, final V, NR, final T. Initial P, initial V, initial T. Like that. The N doesn't change. Let's see what we get. The pressure is under constant pressure, right? So 1 atmosphere, P is equal to P naught, and P naught is 100, and P naught is 101,000 pascals. (101 kilopascal). Okay, let's substitute that here. The volume, let's take a look at the volume. The volume changes. The volume of the balloon after filling is measured 8.5 cubic meter. The helium is heated to 55. It expands at constant pressure. What's the heat flow into the helium, right? So the initial volume is 8 meters, 8.5 meters squared, cubic meters. Temperature 20 degrees C, 55 degrees C, right? So here you go. The initial volume is 5 cubic meter. Nope, that's it. No, 8.5 cubic meters. 8.5 cubic meters. The temperature, initial temperature is 20 degrees C, Final temperature is 55 degrees C. Initial temperature is 20 C. Final temperature, I'm gonna put 55 C. So how we're going to solve this problem, right? Let's put all those numbers in the proper all those parameters in the proper place. Those all they all belong here at the top. They all belong here at the top. Okay. So how do we solve this equation? If we divide this equation here, my initial equation by the final equation, the r is going to cancel out and you don't get your r. Okay, so that's not the way to go. That's not the way to go. We do not know the volume, but we can determine the volume, the final volume, right? We can determine the final volume if you divide those two equations. That allows us to do that. Let's do that. Divide one by the other. And I'm going to solve it for P naught. Substitute right here and determine the final volume. Here you go. Final volume. I found the final volume. And now what do? I know V naught, I know T, I know T naught. What do? I feed this volume back here in the first equation. Okay? I know T, V naught, and T. Going back to this equation, we know R, we know T, and we know V, because we obtained from this equation. What we do not know is N. So we can go ahead, substitute right in here, and we finally get our number of moles in terms of the known parameters. Okay, it's a function of the initial. Let's continue here. P is equal to P naught, right? I'm gonna get the numerical values now. V naught, I'm gonna get my T naught. Don't forget the T naught must be obtained in terms of the Kelvin, right? Kelvin is gonna be 273 plus 20, like that, plus 273, and I have to change the unit here too, right? 55 plus 273. I have to change the unit to Kelvin. Let's go get our R, our T naught. I didn't substitute for P naught yet. I'm going to substitute for P naught right now. And I gotta get my R. What's the value of R? Let's take a look at the value of R. Gas constant is 8.31 joules per mole per Kelvin. 8.31 joules per mole per Kelvin. 8.31 joules per mole per Kelvin. Pascal, let's see if we can change Pascal, the unit of Pascal. What's the unit of Pascal? The unit of Pascal is Newton per square meter. Okay? Pascal is Newton per square meter. Force per unit of area. Here you go. And joules is what? Joules is Newton per times meter. Let's see if we can do better than that. Here you go. Yeah, we got the number of moles of the gas, 352. So let's just review what we did. Okay? So those are the initial conditions. Those are all the initial conditions. Temperature we know, final temperature we know, initial temperature we know, initial volume we know, initial and final pressure we know. We also know that CV for a monatomic gas is 3/2 of R, and the CP ends up being 5/2 of R. We want to find out the heat put into the system. We want to find out the heat put into the system. Okay? So the heat put into the system is NCP delta T. NCP delta T. We know delta T, we know CP. What we do not know is N. Let's find out what the N is. We start with the two equations. I'm going to reorganize that here. Let's reorganize it differently. Here you go. I don't need that right now. We worry about that later on. We start with those two equations, right? Ideal gas law. And here you go. We substitute. I'm gonna make it organize it differently so it becomes clear, right? More clear. Here you go. We start with this equation right here. Those two equations. So the basic equations are the following: this one, this one, this one, and this one. Okay, three equations. What are the unknowns? Unknowns so far. Unknowns are Q, N, and we do not know what's the final volume. We know the initial volume, the initial pressure. Everything else we know. So in principle, we can solve this equation, this system of equations, the system of three equations with three unknowns. In principle, we can solve it. Okay? So let's do that again. I'm going to erase what I had here, and we're going to do that again. Okay, and three unknowns. We need to know, before we solve for Q, we need to know N. In order to solve for N, we have to eliminate V. Okay? So what we do is we eliminate V from the final volume from our first equation. Okay, that's not the way how you do, right? So let me correct it myself. Okay, the way we do that is the following. We divide this equation by this equation. That's one way. But wait a minute. We also know that P is equal to P naught, right? Let's substitute P here for P naught, and let's plug, let's separate my second equation. That's the first equation. That's right in here. And we can carry over this equation, the second equation here, to this other line. What do we have to do next? We have to calculate what V is. We can either, there's more than one way. One way that I like is to solve for P naught. Okay? We can solve for P naught and carry here to the next line. Once we solve for P naught, we can replace the P naught in the second equation. That's the first equation, that's the second equation. Okay? And now what happens? This N is going to cancel out this N. See that? And we can solve for the final volume. That's how you do it. We know T, you know V naught, you know T naught. So by dividing one equation by the other, we get V. Once we get V, we can feed the value of V in the first equation. Okay? Feed the value of V in the first equation, and we get, here you go, two equations, there's still two equations, and from this equation you can get N. Here you go. I'm going to do that right now. So from those two equations, we found V and we found N. So we use two of the three equations to find V and N. And now what do? We place this value of N right in here for Q. Okay? Delta T we know, Cp we know, P naught we know, T naught we know, R we know, and so on. And so on. So let's solve the problem now. Here you go. Delta T, we're almost done solving the problem, is T minus T naught, right? So here you go. We substitute T naught, we substitute T. Here you go. That's what delta T is all about. It's just a matter of getting the numerical values now. Cp we got before. Here you go. P naught we know is 101,000 pascals. V naught is 8.5 cubic meters. And now T naught, we place it right in here as well. Okay, we got, let's get it calculated. Pascal cubic meter. Let's not forget that Pascal is what? Pascal is Newton per square meter. And then you get Newton meters, which has units of joules. Newton meters has unit of joules. Here you go. Let's see if it matches what the book gave us. 2.56 times 10 to the fifth. Oh, wait a minute, there's something wrong here. Did I do something wrong? No. This R cancel out with the R that goes here. So there's no, let's see. Uh-oh. Okay, so I got 256 kilojoules. That's what I got. The book said it's 260. So what do we have here? We have a rounding up from 256 to 260. Okay. So there is no need to find the work done on the gas separately and then subtract it from the churning. Okay, the work done is already accounted for in the molar specific heat at constant pressure. That's a good way of doing it. What about, what if instead air instead of helium? What about air instead? You know, dry air is mostly nitrogen and O2, okay? Diatomic gas. For diatomic gas, so the CV is going to be different, right? The CV is going to be different. So let's see how we do that. All we have to do is to change the CV, not to 3/2, like we did for a monatomic gas, right? But CV for diatomic gas is 5/2. Once we change for 5/2, everything here automatically changes. CP becomes 7/2, and look what we get. We get a Q that 360 kilojoules, 358 kilojoules, okay? And that's exactly what the book has. You know, you rounded it up to 360 kilojoules. Let's do that. Okay, so we did examples for constant pressure. Let's work now the constant temperature situation. Okay, so here we go. Constant temperature. Like I mentioned before, we did that before. That's how we write down the work done on an ideal gas that's undergoing a constant temperature process, an isothermal process. There's some work done in the gas, and the change in internal energy is Q plus the work done on the gas. If VO is greater than VF, this term is positive. If VO is less than VF, this term here becomes negative. Okay? Again, like I told you before, this result here we can calculate using calculus. It's not possible to do that with algebra. You have to know calculus to find out the work done on the gas. Now, let's do this example, right? Here you go. We have a case of constant temperature, and we are compressing an ideal gas. It starts with a large volume and ends with a smaller volume. This gas is in contact with a heat reservoir that's kept at constant temperature. So this heat reservoir has as much energy, as much heat that it has either to input heat to the system or to extract heat from the system while keeping the whole system at constant temperature. If the gas is warming up past 280, this heat reservoir will be able to absorb the higher temperature and cool down the gas to a 280. That's what it does. Okay? So how much heat is exchanged between the gas and the reservoir? Let's take a look here. It's 280 kelvins. We know that the volume starts at 20 liters and ends at 10 liters. And we also know there is an average force of 33.3 kilonewtons used to move the piston a distance 0.15 meters. So that's the distance, how much heat is exchanged. Okay? So let's go there to my software, right? Here you go, all the data that you need. We are tempted, to use this formula here. You can, but it's gonna be too much work, okay? You won't be able to get there either. It's the problem made things easier for you because he gave you the average force. So it's not gonna get you anywhere if you use this formula here. But because the system is at constant temperature, delta U is going to be 0, right? Here you go. Because the system is at constant temperature, the change in internal energy, remember it's an ideal gas, is going to be 0. It's going to be 0. So that delta U that was equal to Q plus W becomes, delta U is equal to 0, right? Constant temperature. Delta U is equal to 0 for an ideal gas at constant temperature. So the heat that is exchanged ends up being equal to minus the work done on the gas. Okay, so how do you... So the work done on the gas is going to be positive because the gas is contracting. And here you go. What's it going to be? You're going to get the average force times the distance that the gas is compressed. 33,300 newtons. Here you go. That's what we get. The work done on the gas. Newton times meter is joules. We can substitute that here. And that's what I'm getting for the work done on the gas. The heat transferred the system is going to lose heat to the reservoir because the system during compression is going to warm up. That's what I'm getting. So going back to the book, I'm getting minus 5,000 joules, which is very close to my number for minus 4,995, right? You go minus 4,995. So that's how we do those problems. Can erase that. And that's what we have for this section of the book. The next one is going to be adiabatic processes, right? Let's do that. No, not this one. Constant temperature. We don't, okay, yeah. You can read this one here on your own, okay? We are not going to do heat engines, refrigerator, reversible engines and heat pumps. We're going to do this one right now. There's nothing much to do here, see? Third law of thermodynamics. It's impossible to cool a system to absolute zero. That's all you have to know. It's impossible to cool a system to absolute zero. And we are done with this chapter number 15. So recall that I ended up covering section 14.4 as well, right? So let's summarize right in here. We didn't do adiabatic processes for ideal gases, so you don't have to worry about that. So going back to the previous lecture. There you go. Material for this lecture. 15 point. Here you can, I want you to read on your own. Read on your own. This one is easy, right? No problem. And what else? What else? We look at also at that chapter, a specific heat of ideal gas. Oh, a specific heat of ideal gases. Is the problem? A specific heat of ideal gases, where the book introduced you CV and CP, right? CV here and CP later on. Okay, that's 14.4 as well. (14.4) a specific heat of ideal gases. A specific heat of ideal gases. I'm going to put this guy here on the top. That's the section where the book introduces. The book introduces CV. Heat, there is heat capacity, a specific heat. Specific heat capacity, right? And molar heat capacity at constant volume. CP is introduced right here in this other one, in this other section. So I see you again some other time. Bye bye.